Hey there, this is part two of our chapter 12 video on the universe. Last time we were talking a little bit about the stages of the sun's life cycle for a star like ours. Again, our star or our sun will have about a 10 billion year lifespan. We think it's about 5 billion years old right now, and it will live another 5 billion years, which is a really long time, right? Um, so here again, we have our sun. It's burning hydrogen, and then as it moves through its cycle, it starts burning more and more helium as well. And then it will start expanding. And so it'll reach this red giant stage in about another 5 billion years. And it elevates Earth's temperature, and the Earth's temperature will increase so much that the atmosphere will be stripped from our planet. The oceans will be boiled dry, and that'll be, again, I expect if, you know, our in future generations, they will have moved somewhere else by that time. And then once it gets to giant stage, there's gravitational collapse. And eventually, we would expect our sun to become a white dwarf. A white dwarf. It's not going to become a black hole, not some sort of supernova. It's just not big enough. So we expect it to become a white dwarf. Um, so again, for a star like our sun, helium fusion continues. Carbon starts accumulating in the star. Again, our sun is not big enough and hot enough to fuse carbon. Some stars are. Some stars are massive enough that they can fuse carbon. Carbon ash starts accumulating inside the core. Fusion starts to decrease. Gravity is going to predominate, and the star contracts. Its temperature boosts, and the color of the red giant shifts from red to blue. And as the sun goes through its final collapse, it ejects plasma and forming a planetary nebula. It's not really a nebula, but sort of looks similar to one. And then the nebula disperses over a million years, leaving the cooling carbon core to as a white dwarf. And again, this is what's going to happen to our star. White dwarf is going to cool for eons until it's too cold to emit light. To emit light. So again, massive stars are going to have a different ending than the slow cooling to a white dwarf. More massive stars, they live fast and they burn up a lot of energy. They have shorter lifespans, millions of years instead of billions and trillions of years. And those high mass stars are brighter. They burn their fuel at a faster rate. The massive star starts contracting, heats up to 600 million Kelvin, begins carbon fusion reactions until the element iron is reached. And then the star runs out of fuel, it cools and loses outward pressure. And then guess what happens? If it loses outward pressure, the star starts collapsing inward like a compressed spring. Then it explodes and forms a supernova. And the supernova comes back together to form a neutron star or possibly a black hole, which is kind of cool. So this is 1987A supernova. Supernovas are the final stage of more massive stars. And it's the collapse and explosion. It's the supernova. And this is a Crab Nebula on the right, and it's a remnant of a supernova. It's just kind of cool. So black hole is what remains after the supergiant star collapses into itself After it collapses, the force of gravity on the surface increases dramatically. It increases so much, that force of gravity increases so much because the gravitation at the surface of the black hole is so intense that light can't escape the black hole. It just that kind of blows me away just thinking about that. All right, so black hole again, the star collapses, gravitation increases at the surface, and it becomes so much that light can't even escape the black hole. Okay, so this is showing some possible stages in the birth and death of an aging star. And here we have, remember nebulae or clouds of gas and dust, and they form that protostar, which has a star in the middle, and then the planets form on the outside. So here we have a main sequence star right here. High mass, it's going to eventually form a red giant and then a supernova and maybe a black hole, or it could be a neutron star. Middle mass is a red giant, which eventually becomes a planetary nebula. Remember, that's not really a nebula, it just sort of looks like one, and that becomes a white dwarf. And then we have stars with low mass, and they become red giants, and then white dwarfs and a cold lump of carbon. Not a black hole, a cold lump of carbon. Right. So let's talk a little bit about galaxies. Galaxies are huge assemblages of stars, interstellar gas and dust as well. Okay, but think of it, galaxy, primarily huge assemblage of stars. Our star is one out of more than 100 billion other stars in the Milky Way galaxy. And the Milky Way is just one of billions of galaxies. So within a galaxy, there are small groups of stars called galactic clusters. Larger groups of stars are globular clusters. So there's a lot of, and I'm really not going to test you on all these different galaxies, but I mentioned them a little bit about the Milky Way. If you're interested, some other galaxies that are closer to us, clusters and superclusters and local group, types of galaxies, elliptical, irregular, spiral, and again, there are billions of stars in these galaxies. Yellow stars are older stars. Again, there's just a lot of, I loved all these pictures, and I probably went way too much into galaxies in my slides, but I couldn't help but include these pictures. So these are showing irregular shaped galaxies, and then let's finally get to the Big Bang. So the Big Bang is a theory that our universe was created by some sort of primordial explosion about 13.7 billion years ago. And it was really hot, about 10 billion degrees Kelvin. Before the Big Bang, there was no space, there was no matter, and the Big Bang marks the beginning of space, matter, and time. Just kind of wild thinking of that. We think that the expansion of the universe is accelerating, and it is pushed apart by a mysterious force called dark energy. That space, again, the space is expanding, so our universe is still expanding. The expansion of the universe is sort of like An ant on a balloon being blown up. I like that example. The ant sees every point in the balloon moving away from it. It's kind of a weird thought. Anyway, again, reading through this chapter, even looking at just looking at it, makes me feel so small in comparison to our universe. So, what's some of the evidence for the Big Bang? Has been observed, and Hubble helped observe this. Dr. Hubble, that the universe is expanding, and he showed that the galaxy's velocity was proportional to its distance. There's a little bit more on Hubble. I have a lot more information and extra slides. I just didn't want to completely overwhelm you in this chapter. Also, scientists have measured cosmic background microwave radiation. This was predicted before it was discovered, and since then it's been measured. And this is the afterglow of the Big Bang. Also, measurements of the amount of certain elements was predicted before it was measured. Helium should be at 24% based on an expanding model of the universe, and that has been confirmed. So what's the difference between ordinary matter and dark matter? So what we think of ordinary matter, we talked a lot about it last semester, is it's protons, it's neutrons, it's electrons that form atoms and combine to make living things and non-living things. Dark matter, we're not really sure what it is, but scientists are quite sure it exists because of its effect on gravitational objects. I have a couple of videos on dark matter if you want to learn more about it. It's kind of interesting. So objects closer to the center of a galaxy, which contains most of the ordinary matter, should orbit around the center faster than objects farther away from the center. So things towards the center should orbit faster than objects farther away from the center, as what happens in our solar system. So the inner planets, in our solar system, orbit faster around the sun than the outer planets. However, this is not what has been observed. Objects in galaxies actually orbit about the same speed, no matter what their distance is from the center of the galaxy. So that's kind of weird. So dark energy, careful measurements of distant galaxies tells us that the universe is expanding faster and faster, and it's accelerating outward. We know that anytime you're accelerating, acceleration requires some sort of application of force. It just has to, right? So the question is, what is the nature of the force causing universal acceleration? And scientists really don't know the answer, but they have given it a name, and it's called dark energy. So anyway, we've reached the end of the chapter. If you want to learn more about Dr. Hubble, galaxy formation, more about different galaxies, there's even more, please look in extra slides. But those, again, that information definitely will not be on the test. And kind of keep in mind with this class, we're going over a lot of material, so it's breadth, not as much depth.